Okay. All right. Well, good morning, everyone. Thank you for joining us back in the CE3220 RC Design. Very happy again to see you all. And I understand today's Monday, but the career starts tomorrow. But if you need to leave early to prepare for anything that you need to do, you can do that. Feel free. And we will have recorded lecture for this one and Wednesday before the fall break. So that will help you to go back review any of the content that you might miss due to this arrangement this week. Okay. And another quick question I have, well, quick announcement and a question. I have posted the practice exam problem on Canvas. Have you guys seen it? Have you guys checked it out at least? Not a whole lot. Let's see some wave of hands, go to reaction, hit a thumbs up or, clap or anything. Give me indication if you look at the practice exam. Anyone? I got a one. Okay, good. All right.
I had no idea it was even up.
Okay, so let me share my screen with you. That's why I feel like may have to make a little bit announcement here today. So, okay, do you guys see my screen? Yes.
Yep.
Okay.
Yes, we do.
So if you go to screen, Canvas, messages. Okay, you go to Canvas. There's a files folder, and you see there's a CE3220 exam 1 fall 2020 sample problems. You open it up, and okay, it's a little bit slow. It should pop up. All right, so you notice that this is last year, fall 2020. It's just pretty fresh, right? And this was the exam we made from both Dr. Sneed and I for 2 sessions. Pretty recent, and this is on code 31819. So most of the stuff that we have covered in this course, this semester, was covered last year. And some of the materials related here. So write your name, of course, you know that. Bring the code, notes, textbook. Now, it was allowed last semester that you guys bring textbook, but not anymore, okay? So this textbook choices was only last semester, well, last fall, because we have the COVID and just a little bit hard for everybody, so we cannot do that. This time we have in person, at least most of the courses. I have about 28 lectures, I believe, counting the last week when I was traveling and this week for career fair. There's only 5 lecture out of 28 will be online. The rest of 23 are in person still, so we cannot allow you guys to bring the textbook. Okay, but A4 creep sheet, that's front and back. Was before front only, but now it's front and back. So enjoy on that. And upload all your full workout solution online using PDF format. This again was last year, the fall, because the COVID was bad at the time, but we'll do in-person exam, okay? So we wouldn't have to do this. All right, so these are short answer problems, right? So multiple choices. We're going to go over them next week, but here today, I just want to quickly glance it over for you if you haven't taken a look at it. So these are very standard questions. Most of the materials from the first problem, problem 1, come from the chapter 1, 2, 3 we have covered in the beginning of lectures, and a little bit more in terms of flexure definition of the Whitney stress block, for example, and some of the stress-strain relationship. We talked about that before, and stress reduction factor, that is the flexure content of it. Okay, and beta 1 and know that. Now you see that there's a cracking moment and effective depth and know that, and provided in this last problem of the problem number 1. And that's where it's going to differ a little bit this semester. We're going to have a workout problem on the detailing of the bars. When I say detailing of the bars, I meant the effective depth, spacing between the bars, height, vertical spacing between the bars, so on and so forth. And I will convert this problem into a workout problem, so make a problem number 2 basically. All right. Okay, so that is for problem number 1. So I have only 5 short problems, but this year I may have a little bit longer than that, so we'll see. Now, problem 2, analysis. So when I say analysis, right, meaning this is not a design problem, meaning you were given the section, you have reinforcement, and you were asked to calculate the moment for it. So this is for AA reinforced section, right, when I have top and bottom reinforcement both. okay? Top and bottom reinforcement both. Like I said, we will not test you guys the design for double reinforced section, but we will test you guys the analysis of a doubly reinforced section. So this is an example of it. So we have 2A, 2B, 2C, 2D, all the subcomponents of the problem, okay? Then going at the end of it, we have problem number 3, design, where we have a section which is at A, at the support, and we would not provide any reinforcement details, and we'll ask you guys to design for it. At the end of problem number 3, you're able and you're supposed to require to put some reinforcement in it, okay, and provide us the capacity. Now, when I do the drawings, right, I want you to know that we are only required to do design for singly reinforced beam, okay, for this type of problem, singly reinforced beam, and we'll tell you specifically, okay, we'll tell you specific. For example, this is right here, the section should be singular reinforced tension controlled and with a single layer, so very specific, okay. Now, mind you that when we say tension controlled, you need to understand the definition of tension control and provide the section correspondingly, all right? Provide the section correspondingly. And of course, right, draw the reinforcement. So that's just where draw the reinforcement, right? Spacing, details, and everything. Now be careful. This is section A, right? And watch out the moment size. Is it negative moment or positive moment, right? So if it's negative moment, think about where the bars is gonna be, okay? Where are the bars supposed to be, okay? All right, so we only had 3 problems last fall, and this year we'll have 4 problems, but I don't see a whole lot of difference. Now, when I say that is because, like I mentioned, I will convert one of the quick question, the short answer problem, into a problem B full workout, just because in the previous semester I got students' feedback say, Bob, this is essentially a full workout problem, but now when I make multiple choices, I only select the choices. If I did wrong, I don't get partial credits. So to help you guys gain partial credits, I will convert this problem to additional problem. So even if your answer is way off, but if your solution process is okay, I can give you partial credits, okay? So that's just a quick rundown what we had from previous semester. So I suggest you and strongly suggest you do these before our review next Tuesday. And like I said again, I'm still confirming the room and I'll let you know as soon as I can. But most likely we'll have a room or we'll do it in my office that I will do this in-person review session next Tuesday where we're going to talk about how we're going to solve these exam problem. And I will not, let me say this again, I will not post the solution to these practice exam problem, but I will go over them and tell you the answers in a way in the review sessions. So, excuse me, do practice the problem and bring your questions to the review sessions. Okay. All right. Let me pause here for a moment. Any question from you guys? Any question from us, folks?
Yeah. Will the review session be recorded? Because I know I have a lab during 3 o'clock on Tuesday. Is that what time you were planning on doing that?
Yes, it will be recorded for sure. And I
Perfect.
will do that in person. So it will be recorded as well. So you guys can go back and review that whenever you need to. Okay.
Awesome. Thank you.
Yeah, no problem. Anything else, folks? Are we happy with this? Well, if you're not happy, sorry, I have to force you yourself going through this because this is what it is for the first exam, okay? Very similar problems, okay? Mallory, I might have to mute you so to cut down any reflections, but feel free to speak out if you have any questions, any comments, okay? All right, so let's carry on, right? Now, before we do anything, homework number 4 is due Thursday, okay? And don't forget, I'm halfway through homework number 2. I finished grading by Wednesday, homework number 3, and by end of this week, I'll finish all the grading homework number 4. So hopefully by end of this week, you should have all 4 homework graded and with my comments. And when I grade it, I usually make some comments on it. If it's calculation error or process error, pay attention to those comments. And quiz, I usually just give you a grade. I will not comment unless there's something too, how to say this, too egregiously wrong, then I have to really go take a look at it, okay? All right, so let's get back to the main content, all right, main dish. All right, so let me share my screen and going over the design for singular reinforced section, okay? Now, design for singular reinforced section. We have talked about design for singular reinforced section before. And last week, when we talk about design for singular reinforced section, we mean design for reinforcement. But last Thursday, when we talk about design, we actually meant to design an entire section without knowing anything. That means no geometry, no reinforcement, no nothing, right? So to design that, we went through some design methodology or philosophies. We firstly define a new term that is called rho, the reinforcement ratio, all right? This is very important, and I'm labeling as a star, so you know that this is important. So rho is equal to AS divided by BDS. Now, pay attention, folks. This AS, you see, it doesn't have a prime on the side. So it means the tensile reinforcement. If I have AS prime and BDS again, and I'll call it rho prime, and that is a compressive reinforcement ratio, okay? Compressive reinforcement ratio, all right? So here, what we mean are mainly for tensile reinforcement ratio. They're different. They're quite different, okay? So prime or no prime, you see the systematic symbols throughout the lecture notes. When you see a prime, most likely it's compressive. When you don't see a prime, that is tensile, okay? Now AS over BWDS, BW is the web width, is the minimum width of the section, right? You know it for rectangular, easy. For I, for T, it's just gonna be the web, okay? So be careful on those. With that, we'll bring and show the strain diagram, stress diagram, the internal forces for a typical section, singular reinforced section. And we said, again, this is very important. You may see this in the first exam, is that to set this design state, okay? I cannot emphasize this enough. Design state meaning the state of the strain and the bars we want to achieve to do design, right? So we want to make sure the strain in the bars at the level of 0.0075, which is much higher than the strain typically required for tension control. So that is our design state. So if I ask you in the first exam, problem number 1, what is the design state for singular reinforced section? You need to know that is a strain at level 0.0075. Okay, then from there, we go and find out the actual compressive zone C, find out the compression force of CC, and eventually got this equation here where rho is equal to 0.24 prime C beta1 over Fy. And we said, because we're civil engineer trying to keep everything clean and neat, so we approximate 0.24 as a process 0.25 and convert that to be 1 over 4. Here it is, right here it is rho initial, and this is again very important, is the initial estimation reinforcement ratio in the section, and that is beta 1 over 4 F prime C divided by Fy. Okay, now this equation should and will appear in your crib sheet because you need it. Okay, you need it. And then going from there, we introduce another terminology. It's called a reinforcement index. Again, folks need to remember that omega, and omega essentially equal to rho multiplied by Fy over F prime C, and is just the beta 1 over C, 4, sorry, beta 1 over 4, okay? And again, all these star marks, meaning they are important, need to write down the crib sheet, and you see them in the exam again, okay? Now, when we have this omega, bring into the equation, and we now know that when we have A, the effective compressive zone can be rewritten in terms of reinforcement index omega, and that is omega ds over 0.85. But that is not into the world, right? We bring in this A into the moment capacity equation and calculate the moment resistance, and we find out that Mn equal to omega prime C bracket inside 1 minus 0.59 omega outside bracket BDS squared. And folks, we put this whole thing as a bracket and call it what? The flexure resistance factor. Flexure resistance factor. Again, this is very, very important, right? You hear this word a lot. Bob's going crazy and keep telling it everything is important. Yes, because you need this equation for your calculations. All right, so now I have R, and eventually I convert my moment capacity equation as Mn equal to R BDS squared. R BDS squared. So might as well put an emphasis on this, because this is also very important. At the end of the day, we end up with the equation that BDS squared has to be greater than or equal to U, be careful, this is MU because we're using the design equation here, and here MU over phi R. So you look at this equation, you realize that this is basically our design rule, right? Design guide or design rule. Okay, and again, you put this down as the equation. Put this down as the equation. Okay, so now this is our design equation. So how are we going to design a section? So this has become easy now. Let me go back and continue here. So if we say let the width of the section B is a certain ratio of the depths, and I call this ratio to alpha, right? Knowing that alpha is a ratio between the width and depth, and that is also ranging between 0.5 and 0.8, meaning the width of the beam is usually between half or 80% of the height, or sorry, depth of the beam. Okay, be careful, this is not H, this is depth, ds. All right, so this is what we call the design parameter. Okay, design parameter. All right, and now with that, I can go back to this equation and find out that alpha ds cube, bring this in, alpha ds cube has to be greater than or equal to mu over phi r. Mu over phi r. Now, with this, I can further write this equation down as ds has to be greater than or equal to mu divided by a alpha phi r, the whole thing to the power of 1/3, to the power of 1/3. And ladies and gentlemen, this is the key equation to estimate what? The depth of the section. And this is our equation 8.5. The depth of our section. So this is saying that if you were given the apply moment capacity to the beam, or sorry, apply moment to the beam, and you want to estimate the depth of the section, you use this equation. You use this equation. All right. And for this, several notes here, okay? Several notes here, very important. A or 1, we can always assume, the strength reduction factor phi is approximately 0.9. Okay, always assume that. And also, we can always assume the depth of the section ds is equal to h minus 2.5 for one layer of reinforcement, and ds approximately equal to h minus 3.5 when there's 2 or more layer of reinforcement. Okay, all right. So with this, we have our design rule. How to design a section if I don't know anything. Okay, so I'm confident that I can do any problem right now, right? So let's take a look at an example. So example 8.1, first example in the design problem. I want us to design a RCB, okay, with a simply supported condition. So let me just make a very simple assumption, simply supported condition, okay? Simply supported condition, and mu, and I give you the apply moment, that is 153 kip-foot, okay? And span cross over a 28 feet, all right? And with a concrete compressive strength of 4 KSI, curbside concrete, you know, and then grade 60. All right, my first victim. You all think you might dodge the bullet, right? It's not so many people, and Bob's a little bit Monday, right? Maybe not yet fresh, but let me pick my next victim. Who's talking? Tagoda? Smart?
Yeah, hello.
Hey, how are you doing, man?
Doing good.
Doing good, okay. So what is the yield strength for grade 60?
It'd be 60 KSI, right?
All righty, good deal. Wonderful. Okay, thank you. That's it. All right, so with that, I start my design process. Okay, I start my design process. So where to start? Actually, let me put the beam down so you have a visualized picture, right? So I have a simply supported beam. I say the span length is 28 feet. All right, And now with this, right, naturally you can think of it, usually the maximum moment happen in the middle span. And this is where the maximum moment is at 153 kip-foot. Okay, all right. So with that, the first thing we want to determine is actually the section size or section dimension. So something I haven't mentioned before, and this is where it becomes important, is that I want to estimate the height of the section. So how do I estimate the height of the section? Before you do anything, let me share you something else before we do this design. Okay, so go back to the canvas. There's a file folder, and sometime last week, Thursday, I uploaded tables called table 9.3.1.1 from ACI code. Okay, so you open this table, you say that it is minimum depth. Okay, minimum depth of non-pre-stressed beams. So that is DS, isn't it? That is DS, isn't it? So based on different support conditions, simply support it, one end continuous, both end continuous, or cantilever, I can determine my minimum height. And be careful here, okay? This is H, all right? This is H, okay? So this is, although it is depth by the table, but this is H, okay? Be careful, okay? Be careful. Now H should be L over 16, L over 18.5, L over 21, L over 8. What is L? L is the span length. Span length. So this is saying that actually, if you know your span length, which in our case we do know, and for a simply supporting condition, we can estimate the height of the section, which is L over 16, right? So with that, okay, I say fine. Based on ACI, I can do that. So let me share back to the screen, and we can estimate the number to start with as my height. Estimate number to start with is my height. And going back and look at this, I say, look, I want to do some estimation, and I pick a number, say H, right? Based on ACI code, and let me just say, put it here, ACI 318.19, 9.3.1.1, and that is a table. It says that H should approximately equal to L over 16. L over 16, okay? And then I say that for the sake of safety, let's, instead of putting this, let's put a range on it. Okay, so I say H better be picked within a range of L over 12 and L over 18. L over 12 and L over 18. Okay, all right. So if I do this, right, this still covers L over 16, right? Still covers that. And I bring L over 28 feet. Okay, and avoid confusion. Let me just use capital L so you know that. And I can get my H has to be between 19 inches to a 28 inches. Something I had to start with, right? So this is the range of the height. This is the range of height. So I don't do anything. I just want to provide it right here. It's like when you sign a contract, there's hidden clause, right? You don't see them. They're hidden somewhere, very small font, but they can come back and get you at the end of it, right? So we just put down here, say, okay, that's fine. Now I have a bound, or I have a range of height I can work with. But then we start the next very important step, is to estimate the initial reinforcement I have in the section. So row initial, and row initial right now.
I have a question.
Yep.
How can you say it could be between L over 12 and L over 18? Because L over 18 would put out a smaller value than L over 16.
Oh, isn't it? So I've switched. This better?
Yeah, but I guess I still am confused, because if you use L over 18 versus L over 16, you're going to get like 19 versus 21 inches. And if you're going by the code, wouldn't you have to use at least 21 inches?
So L16 should be between 18 and 12. Is that right?
Where are you picking 18 and 12?
This is from other things from ASCE.
Okay.
Yeah, but what I'm saying is you can use this here from ACI 9.3.1.1 table, and that gave you an exact number, but be careful on this. This is what we call the minimum, right? And if you notice in the table, there's a small notation mark here, 1, and that is different because this one H is so-called effective depth, and that depth changes when you have different support conditions. Okay, all right, so that is to say that this L/16 is not really accurate. Okay, so I usually do not pick a number directly from there. This is so-called minimum, means you can go higher than that. And again, their definition of H in ACI code is not the same definition of H in our section. Okay,
Okay, so I guess what I'm confused is if H/16 is the absolute minimum, why would you pick H, or why would you pick L/18? Because that'd be
yes,
smaller than L/16.
yes, so that's what I'm saying. So the H definition here is not exactly the same definition as our section high H.
Oh,
Okay, so the notation one, as I keep saying just now, if you look at it, there's a clause. Let me just put out here, okay? So let me be careful with that. That's a very good point, by the way, okay? I think this is a very good question. You see this table here, Mike?
Yep.
And there's a small one here, can you see that?
Mm-hmm.
And it says how expressions applicable for no more weight concrete and FY 60 KSI for other cases, minimum H should be modified in accordance with this, and as appropriate, right?
Okay.
Yeah, so this means this minimum H is not always the H we're talking about. You see it? Yeah. So my 18 and 12 estimation mainly come from my experience in ASCE code as a beam deflection criteria. And that has, how to say this, that has something to do with design philosophy, because if your height is too deep, then you don't have a beam type of behavior for your structure members. So you cannot call it beam anymore.
Okay.
Got it? Yeah. Okay.
Yep.
So that 18 and 12 is my experience, and simply say that my 18 and 12 covers this. Is that right?
Mm-hmm.
Right. That better or still confused?
I got it.
Okay, good deal. Okay. Yeah. So again, you're right, Mike. I mean, that is different from what ACI says, but now pay attention here as well. Let me share my screen. And I want to say this is a very good question, folks. You should follow this. Is that, do you see that I did not provide any H? Right? I just provide a range. I did not specify what is H, right? Mike, do you see that? Hello?
Yeah.
Yeah, okay. So the reason is that I just want to provide a range here, but I will get my H from the rest calculation and go back and check it. So that is to say that at least make sure H falls in this range.
Okay.
Yeah, so it doesn't have to be exactly 1/16. Actually, that is an estimation when you don't know any information. Okay, because this is a meteor step. In the end of it, we'll talk about it later half of the lecture. We have to calculate deflection of the beam. Where there, we need to check your H again. And that actually will determine your H more rigorously than just the capacity right now.
Okay.
Yeah. Okay, clear?
Yep.
All right, good deal. Okay, thank you for bringing this very good question. Okay, so let's just put this range here without going through detail and knowing exactly what, but the next step is very important. We got to find our initial reinforcement ratio. All right, so remember the equation we talked about before. So this is beta1 over 4 and multiply f prime c over fy. Okay, now beta1, given the concrete stress of 4 KSI curbside concrete, and this is 0.85 divided by 4 and multiply f prime c at 4 KSI and then grade 60 KSI. And now I got a number of this and save you the trouble calculation, 0.0142. Okay, now quick thing here. Mike, well, I'm having you here. What is the unit for a row initial?
It'd be unitless, wouldn't it?
Exactly, so that should be unitless. Okay, very important. All right, so make sure KSI cancel. Thank you, Mike. KSI cancel, and this is unitless. All right, okay. So this is rho initial, and now I can get my omega. And omega, don't forget, it's called a reinforcement index. Okay, and that is rho initial multiplied by Fy divided by F prime C. But it is also beta 1 over 4. Okay, so that is roughly equal to 0.21. And again, unitless. Okay, unitless, no units, very important. Okay, now why I say these are very important, because we have introduced 3 items, 3 terminologies, and last one, especially important one, is called R, is called flexure resistance factor. Okay, flexure resistance factor, and R equal to omega and multiply 1 minus 0.59 omega, and then multiply F prime C. So fellows, front of it, these are unitless. Unitless, that's fine. We understand that, but F prime C has unit, and it has unit as PSI. Okay, so when I do this, omega equal to what? 0.21, and multiply 1 minus 0.59, multiply 0.21, and then multiply 4,000 PSI, folks, 4,000 PSI, okay? Not KSI anymore, okay? I want to use PSI. So I got my R equal to 736 PSI. All right, so very, very important, okay? R is actually kind of equal to an effective tensile strength of the RC beam, not the concrete, but after steel put into it. Okay, so that's, you can think of it. And this is very important. R does have unit, and has the same unit as the unit of prime C. Okay, and this is very important. And with that, I can do my calculations. Now things becomes a little bit easier. We can assume, again, alpha is a ratio between the width and the depth. Now this has nothing to do with height yet. Okay, nothing
Is
to do with
there a
that yet.
reason you chose to do PSI instead of KSI?
Yes, because what is the tensile strength of concrete? Roughly 1/10 of a prime C, right? So if I have 4,000 PSI of concrete, tensile strength is about what? 400 PSI, right? Remember? FCT, FR type of thing. So I always want to see my R, because R is kind of effective tensile strength of the RT section. So if usually R is between a range of few hundred PSI to 1 or 2 KSI, 1,000, 2,000 PSI. So if my number comes out a little bit different, I will know I made a mistake there. Does that make sense?
Yeah.
Okay, so in a calculation point of view, it doesn't really matter, right? I mean, 736 PSI is kind of like 0.7 KSI, is that right? Right? So it doesn't really matter, actually, right? But the point is that I got a feel of what R is supposed to be, so I use PSI. Okay, all you have to do here is that you can use 4 KSI, but make sure you know when this roughly compared to FCT. And I can tell you, right, this must be higher than FCT. Right? Because it's effective reinforced concrete section tensile strength. It has to be higher than the concrete without any reinforcement in it, isn't it? Does that make sense, Ashton?
Yeah.
Okay, good deal. All right, good deal. If it doesn't make sense, don't let me go, okay? I want you guys to understand, okay? So just keep drilling at me. I like it. Okay, that's good questions. Now, alpha has to be between the range of 0.5, 0.8. And again, this is design practice. Okay, of course, you don't have to follow that, but this is good suggestions. Good suggestions. Okay, so I'll pick a number and say let alpha equal to 0.7. Okay, why, Bob? You know, I like 0.6, 0.7. It's just proportional in my head, because now if I do edit the height of the ds. So essentially I get about 1/2 of a width. So, okay, so this is a little bit stretching a little bit beyond. So I prefer my section has a 1:2 ratio. That means B and H is a 1:2 ratio. All right, but BDS, right? Usually I get about 0.7 or 0.65 sometimes. So that's just me, okay? That's just me. All right, so I pick this number. I say, okay, DS now, given alpha equal to 7.7, and I bring all the way back to the equation here, trying to find my depths, right? So DS now, let me recopy this equation, should be greater than or equal to mu divided by alpha phi r to the power of 1/3. The power of 1/3. Now, bring the number in ds, then has to be greater than or equal to mu 153, keep foot, and then multiply by 12 inch per foot. I'm converting everything back to inches, divided by alpha. Now I pick 0.7, okay? Again, this is a pick by me, okay? And this is phi 0.9, and r, remember, that is 736 psi, okay? But you see that I have, okay, I have kips here. So here, Ashton, where you are having the question, I can now use 0.736 KSI just to cancel the unit. All right, and don't forget outside 1/3. Okay, now here, folks, please help check my calculation. Okay, I made this calculation last semester and I checked it last night, but I'm not sure. I got 15.8 inch. I gave it a little bit more time. Help me verify that because I don't want to make any more mistakes. Okay. All right, guys, pull your calculator out. Let's see what you got. Anybody get this number, 15.8 or differently? Anyone?
I got that number.
You're gonna have good deal. Okay. So if you get a different number, let me know. If not, we're just gonna carry that mistake with another friend of mine and then continue ds equal to 15.8. Now, ds right now is 15.8, but I'm going to choose a different number again. All right, why is that? Okay, so I want a ds that has to be greater than 15.8. Okay, but 15.8 is odd number, it's a strange number. So the next I would go to is 16 inches, isn't it? Is it? And Mike, this is for you, okay? Now, if I do 16 inches, I need to think about the reinforcement I have. I have h, which is section height. I always want the integer for section height. Why is that? Because standard formwork and all, right? Formworks are usually integers. It is very hard to have a half-inch formworks. So if I think about it, ds and height relations are usually point to 2.5 or 3.5. You see, there's a 0.5 number here. It's very odd, right? So if I have an integer for ds, 16 inches, I end up 18.5, 19.5 a section. It just doesn't sit right with me because I want h to be integer. So that's why I say, you know what? I'm adding a 0.5 inch. Okay, but another trend, the subtle detail here, you realize that I always add, I don't subtract. Let me say this again, very, very important. I always add, I don't subtract. Why is that? Because the taller the section is, the higher JD is, and the higher JD is, less reinforcement I have to put into it. If the same reinforcement I'm putting into a higher section, I end up with larger moment capacity anyway. So always go higher. Okay, all right. So with that, I say ds equal to 16.5, then h equal to ds plus 2.5 inch, and voila, perfectly, I got 19 inch. Right? So some of you say, Bob, look, it's 19. It's 19, right? Why can't you make a round number, right? Again, I say, you know what, that's fine. I'm gonna go with a wholesome number, h equal to 20 inch. And don't judge me, and this is just me. I want to make it easier for my construction folks. Taller and wholesome number, 20, right? It's just better than 19 because I know there's a formula for 20 inches. I don't know about 19, but I know there's a formula for 20 inches. That for a fact, right? So with that, I finished my step number 1. So what we have done so far, we have done is that we have gone through 1 and 2. We come out with h equal to 20 inches. And this comeback check here is higher than the 19 inches. And Mike, can you do a quick calculation for me and see 20 over 28 feet? How much of a ratio we have there? This is h over L basically.
You say 20 over 20 feet?
28, right?
Oh, okay.
Yeah. What is it?
0.06.
So let's do a 1 over something, right? So 4, I got a 5, I got 3. So it's 5 over 3/8. Something like that, right? So I got this 1, I got this 5, 1, and 34, almost like 17 approximately. So this is approximately 1 over 17. Does that close? Can you check me, Mike? 1 over
Yeah,
17?
it's
Yes.
like 1 over 16.8.
Yeah. So 1 over 17.8, right? Something like that.
16.8, yeah.
Yeah. So something like 1 this. That right? All right.
Yep.
Okay, good deal. So you see this number is not ACI number, is that right?
Mm-hmm.
But it's close. Okay. So like I said, you don't have to be exactly on money for 5 to 7 years. It doesn't have to be exactly as ACI says, but within the range. All right, within the range. Okay, so just a little bit subtle detail. Come back with this now. So we're happy with h to 20 inches, but it's not done yet, right? So now I'm looking at a section of height just 20 inches. Okay, now what about B, right? What about B, right? So supposedly, remember we said here, let alpha equal to 0.7. That means B over ds equal to 0.7, right? B over ds equal to 7. That means B over h minus 2.5, assuming it's 1 layer equal to 0.7. And h is 20 inches, right? So I can probably get h 20 minus 2.5, 17.5, and multiply by 0.7. Then I got some number I'd be done with, right? I can call that B, right? And you know, Bob, like you keep playing, you just add a number up, make some wholesome number and call it good, right? No, I'm not going to do that. I am not going to do that. Why is that? Because all these work, and you will start to get used to this in concrete world. All these work on only estimations. So the name of the game is you guessed something and then clear it up, erase your memory, start from the get-go. Start as you don't know, as if you don't know anything. All right, so let's start all over. I have h equal to 20 inch. Don't know how I got there. What I did, fine, h is 20 inches now. I have to redefine or recalculate my width. So this is the second step, find B. Okay, this is more iterative process. You see a lot of iterative process in design for concrete design, okay? So with that ds for a singular reinforced section has to be h minus 2.5 inch, right? We know that. And 20, again, this is 17.5 inch. All right, and we do not use the alpha anymore. Instead, we say, look at the equation BS squared, remember, has to be greater than or equal to mu over phi r. So you can run it and B has to be greater than or equal to 9.1 inch. All right, so we're using the design rule, design equation again. Here is 9.1. Again, now I can play the Bob's game and say, Bob says, you know, set B equal to 10 inches. I don't want 9.5, it's just ugly. And, you know, remember what I said? I love a wholesome number, and also I love the goal ratio of 1 to 2, right? 1 to 2. So now I'm ending up a section with a section that now at step 3, again, you erase all your memory. I say, I forgot everything I did, right? And now somehow I got a width of 10 inches and height of 20 inches. Magically, don't know how I got there, but this is it. And then at this step, what you do? Okay, I'm gonna pick my next victim. Okay, I think I could gotten J. Let me pick Jessica, Miss Rhodes. Are you there? Jessica, are you there?
Yeah, can you hear me?
I can hear you. Don't be nervous, okay? So
Okay.
quick question here. I got my section dimensions 20 inch of height, 10 inch of width, okay? And remember, we're designing for a reinforced concrete section, right? So my section is determined. What is undetermined? When you look at a reinforced section design, right? We have the section dimension.
Yeah.
What is missing here? We give you a
I
hint.
guess we don't know DS, but do we
So
assume it again?
yes, we don't know DS, but where DS coming from? We need to know what?
Uh,
The reinforcement, isn't it?
I like the type of reinforcement.
Yeah, anything. We have no information on the reinforcement, isn't it?
Right.
Right, that's good. Thank you, Jessica. That's it. So we don't know the reinforcement. Okay, so here, since we don't know the reinforcement, but we know that MU has to be what? Let me see here, from all the way up from top, 153 kip foot, 153 kip foot. That's the capacity I need to meet. And I have what? The concrete 4 KSI curbs on concrete and yield strength of 60 KSI. Jia Hao. We're down to J. Jia Hao, are you there? Jia Hao? You left us? You there?
Yeah, I'm here.
All right. Quick question for you, sir. By the way, how are you doing? Doing okay?
Yeah, I'm okay.
All righty. So now, if I have the section side 20 inches height and 10 inch of width, I have MU F prime C4 KSI FY 60 KSI. Do we or have we seen this problem before? Have we seen the problem before?
Yeah, I think so.
This is what? This is for design reinforcement for what? A known section. Is that right?
Yeah.
So we talked about this last week, right?
Yes.
Okay. So that's what it is. Okay, that's what it is. So now the rest of the problem should be easy. This is design a section with design a known section without reinforcement, giving you MU everything, right? So this is our quiz number 7. I want you to practice this problem. Okay. Okay, so finish this. Okay, finish design for AS. All right. Okay, before I continue, any questions? Anything? Anything?
Yeah, when will quiz 7 be due?
Quiz 7 be due next Monday after the fall break.
Okay.
Let me check when is that again? Give you a week, so Monday, October 4th. Okay. Should have enough time. This is a simple thing. We've done this before. Okay. All right. All right, folks. This is it for today. Okay. So we're going to cover T-beam on Wednesday, and this week we'll be ready for the exam for next week. Okay. We'll talk about T-beam on Wednesday, singular reinforced design again, and we'll be ready for exam next week. Okay. So I'm gonna pause here, and Mike, you want to stay because you got questions, right? Mike, you there?
Yeah, I'll stay on.
Yeah. Okay.
Yeah.
So rest of the folks, please welcome to stay, to listen in, or you have any other questions. Okay. And if nothing else, I'll see you on Wednesday. All right. Thank you so much.